Come on, guys. Yeah, thank you. Good morning, guys. Hello. Can you hear me, guys? All right. If you were not here on Monday, if you did not get this on Monday this week, could you please see me after this lecture? Right? If you did not get this, if you don't have this, please see me after this lecture. Right? All right. I just want to revise. I just want to talk about what we talked about on Monday. On Monday, we talked about what is statistics. Yeah, you're right. Yeah, I think it's working good now. You okay? Is it on, sir? Can you see if it is on? Can you see, is it on now? No, it's not on. Okay.
Double check the battery. The batteries will go on you, then you replace.
It's on now. Thank you, sir. All right. Shh. Hello, guys. On Monday, I told you what is statistics, right? I talked about the meaning of statistics. This is one of the statements by a philosopher named H.G. Wells. The popular trend in statistics. These are some of the current topics. Then I define these four terms which are fundamental to statistics. The population, the sample, the parameter, and the estimate, right? I gave a couple of examples. This is example 1. This is example 2. Then I talked about two different sampling schemes. One is simple random sampling with replacement. The other is simple random sampling without replacement. Right? I mean, these are two of the simplest sampling methods. But there are others, of course. I will not talk about this in this course because there are so many others. There are so many other sampling schemes that I could as well teach a course on sampling. Yeah. Okay. Right. And well, I gave you two examples of one for the simple SRS with replacement, one for SRS without replacement, right? And then finally, I talked about variables, quantitative variables and qualitative variables. Quantitative variables are like things like age, height, weight, and so on, and qualitative are like color or ethnic group is a qualitative variable too. All right. So these are stuff we covered on Monday in case you forgot, guys. Okay. Now today I'm going to talk about quantitative variables, right? I'm going to talk about quantitative variables. There are two kinds of quantitative variable. One is could you listen, please? There are two kinds of quantitative variables. Loosely speaking, they are known as continuous variables and discrete variables, right? Continuous is, for example, weight is a continuous variable. Height is a continuous variable, and so on, right? Examples of discrete random variables, for example, number of scores, number of scores is like in football, for example, and the number of goals scored in a football match is a discrete random variable. It can be 0, 1, 2, etc. Right? So number of accidents. Say the number of accidents in a particular junction in M4 will be a discrete random variable. It can be 0, 1, 2, etc. So these are examples of discrete, and these are examples of continuous random. I'm sure you know this stuff before now. This must be pretty easy for you guys, right? Right. Now, the next thing I'm going to talk about is, by the way, the quiz 1 is due Monday. So you should have already done quiz 1. Please give it to me after the lecture today, or after the example class later today from 3 to 4. And quiz 2, I have already put the quiz 2 online. So if you go to the course website, you will see quiz 2 is already online. Okay, and it's due on the 11th of February. Okay. All right, guys. Now, the next thing I'm going to talk about is how do we define the probability structure of, suppose you take continuous suppose you take a continuous random variable. How do we define the probability structure of a continuous random variable? I'm sure you know this, right? So let x be a continuous random variable, right? Okay, then the probability structure of x is defined by the probability structure of the variable x is defined by something known as the probability density function, or short PDF, right? Okay. And then something not this CDF, there's also something known as the CDF, which I'm sure you know. It means cumulative distribution function. The CDF of X is defined as follows. It's denoted by capital F subscript X, and it's equal to the integral from minus infinity to X of F X Y dy. So this is the definition of the CDF of a continuous random variable, right? The mean of X, the mean is the same as the expectation. The mean of X is defined, well, it's denoted by E of X, or the expectation of X, and is defined to be this. Okay? All right, and the next one. The next one is the variance of X. The variance of X is denoted by VAR of X. Yeah? Okay? And well, there are multiple forms for I'm sure you know this. It can be written as the expectation of X minus the expected value of X squared. Okay? This is one formula for the variance of X. Another formula is, this can be simplified to the expectation of X squared minus like this, right? Okay, and this, of course, if X is continuous, if X is a continuous random variable, this is simply all right. So this is the definition in the continuous case, right? All right, guys. Now, finally, the nth moment. The nth moment of X is defined as, well, it's denoted by the expectation of X power n, yeah, and is defined as the integral from minus to plus infinity of okay. All right, guys. So this is all in the continuous case. And also, I want to mention, if you have So I should, if and only if the following happens, that the probability of x1 less than equal to x1, x2 less than equal to x2, up to the probability that xn less than equal to xn is the product of the probabilities that xi is less than equal to xi. All right? So I should remove this term if we don't need this. I mean, so in other words, this is the product of capital F xi at xi. Remember, the CDF, the cumulative distribution function, is simply the probability that the random variable is less than or equal to the observed value, right? You guys okay? Yeah. So that's in the continuous case. Now, in the discrete case, suppose you're right, guys. There's no need to. You're not okay. What's the problem? Oh, come on. You don't need to write this down, madam. I will scan things. I mean, as I said to you last time, after every lecture, I will scan the notes and put it online. So if you go to the course website, you will see the podcast as well as the scan notes, right? Okay. Otherwise, you know, it. So the next thing I'm going to talk about is discrete random variable. All right. So let x be a discrete random variable. All right, guys. Then the notation, the probability structure of x is defined by something known as the PMF, which stands for the probability mass function, right? Right? So that's the probability mass function. The CDF, which is the cumulative distribution function of x, is defined as follows. Because in the discrete variable, we cannot use integration because it's defined only on discrete intervals, right? So you have to do summation, not integration. So you do the sum all right. So this is the definition of the CDF for discrete random variables. Yeah, and the mean of x or the mean of x is the sum. You guys okay? It's the sum of the x multiplied by the probability mass function over all values of x, right? And the variance of x can you guys in the back see what I'm writing? Okay, is it large enough? Okay, good. So the variance of x is, for a discrete variable, is the sum of x squared times the probability mass function over all x minus right. So this is how you define the variance for a discrete random variable, right? And next, the nth moment. The nth moment of x for a discrete random variable is defined like this. Right, this is the nth moment, right? And furthermore, that we say that if you have random variables x1 to xn, right? You say that if you have random variables x1 to xn, and if they are independent discrete random variables, if and only if the following holds. Okay, so that's about independence, guys. Right. The next thing is, are you guys okay so far? Right. Okay. The next thing I'm going to talk about is you have a question, sir?
Yes. What is the moments of x? What does it represent?
Well, when n equal to 1, it is the mean. When n equal to 2, it can be used for the variance. For n equal to 3, it can be used for skewness. And n equal to 4, it can be used for kurtosis and so on. So, yeah, n is just a power, yeah. It can take the values 1, 2, 3, 4, etc. Yeah. Any other questions, guys? Right. The next thing I'm going to talk about is, I know you might have done this before, but properties of mean. Can you listen, please, guys? Well, the first property is A, the expectation of a constant is itself, right? The second property, B, the expectation of a constant multiplying a random variable, say x, is C times the expectation of x. Yeah? And C, the expectation of a constant multiplying a variable x plus another constant d is equal to okay. So these are some properties of you might have seen this before, as I said, but they're not difficult to prove, right? So for example, if you want to prove A, right? Yeah, okay, let me assume for the sake of the proof, let me assume that the variables are continuous, but the proof is the same in the discrete case. Right? So right? Now this must be 1, because as you know, any density function must integrate to 1, right? So C times 1 is C. So that's the proof of A, right? And proof of B right, to prove B, you do it like this. You start with the expectation of this, yeah? And this is the integral yes? And because C is a constant, you can pull it outside the integration, right? So this will become C times the integral right? Now, just a minute ago, I told you that the definition of expectation for a continuous variable is simply this one here, okay? So what you have is, so the proof is complete, right? You guys okay? Yeah. Oh. All right, and finally, the proof of C. So to prove C, you start with expectation of Cx plus D. Yes? So this is the integral yes? Right. Now, because you have a sum of two different terms, you can decompose this integral into two different sums, right? So you can write this as C this, plus D like this, okay? All right, now what you have here, the first term is simply C times the expectation of X, and the second term is simply D times 1, because as I said, the integral of a PDF must be 1, right? So what you have is C right? Is that clear, guys? Any questions? Right. I'm disappointed that nobody zoomed me so far. I mean, my Zoom is always open, so if you have any questions, just call me, right? I mean, I only meant it as a joke that you had to call from your shower or something. I didn't mean it. Yeah. I mean, any questions you guys have, you can call me from anywhere. Yeah. Yeah. I always keep my Zoom open, so. Yeah. Right. Yeah. Come on, guys. All right, let's now talk about properties of variance, right? The variance of a constant is equal to 0, right? I'm sure you know that. Number 2, the variance of a constant multiplied by a variable is c squared times the variance of c, variance of x rather. Yeah? And number 3, this is the same as c squared times the variance of x. Okay? And the proof of this is not difficult again, once again. Right? You can, it's easy to prove. All right, the proof of A right? The you guys listen, please, right? So the proof of A, I'm just using the property that the variance of a variable is x minus the expectation squared, right? So now we proved just a minute ago, I showed you how to show that the expectation of a constant is constant, right? All right, so that's easy, right? So that's how you would prove that the variance of a constant is 0, right? Right. Number 2, are you guys okay? Any questions so far? Proof of B. variance of c times the c times the variable. By definition, this is this, yeah. And this you can write as the expectation of Cx. Now, from what I proved a minute ago, the expected value of C times x is C times the expectation of x. You follow me? Okay. Now, the C you can pull outside, so this becomes the expectation of C squared yeah. Okay. So now I'm going to pull C squared outside the expectation, which you can do because of what I just proved. Right? So this is going to be C squared times the expectation of okay. And finally, this is C squared times the variance of x. All right, so we have proved that the variance of constant times x is constant squared times the variance of x, right? And finally, proof of okay, we want to find the variance of Cx plus d, where C and d are constants, right? So this is going to be this. Yes, by definition, this is equal to this. Right? Now, from the thing that I proved for the properties of mean, you can write this guy here as C times the expectation of x minus d. Right? Okay, now, you with me, guys? The d and the d cancel, right? So what you have is the expectation of Cx yes? Okay. Now the C you can pull outside because it's a constant. So this becomes C squared okay. And finally, this is equal to C squared times the variance of x. All right, so we proved property 3 of variance. All right. Any questions so far, guys? Yes, no? Okay. The next thing I'm going to talk about is the mean. Right? Suppose Do you guys know the meaning of the word random sample? You know, the word random sample means the following. It means right? The word random sample means that x1 to xn are independent random variables and they are identically distributed. You know, I've been teaching a second year statistics course for the last 10 years, and when I ask the students what random sample means, they don't know. Now, when you guys go to the second year, make sure you know, right? Okay. Okay. Right. Now, right? So let's suppose that the mean or the expectation of xi, this is I, guys, okay? So the expectation of xi is mu, and the variance of xi is sigma squared for I from 1 to n. The mean is defined by, I'm sure all of you know what the mean is. The mean is the x bar. It's denoted by x bar and is defined to be the sum of the x's divided by the number of x's, which is n, right? Okay. Now what I'm going to show you is, I'm going to show you what is the expectation of x bar, in other words, the expectation of the mean, right, is the expectation of this guy here, right? Okay, guys. Now this you can write as one. You can pull the n out. N is a constant, so you can pull it outside, and you can write it like this. Okay, you can write it like this, right? And now we know, we are assuming that the expectation of xi is equal to mu for every I. So this is going to be 1 over n times mu, and this is going to be mu. So the expectation of the mean or the sample mean is equal to mu, right? And I'm also going to show you how to derive the variance. The variance of x bar. The variance of x bar is the variance of is the variance of this, right? And because x1 to xn are independent, remember we are assuming that x1 to xn is a random sample, which implies that they are independent random variables, right? All right, therefore, we can, when you pull the n outside, n being a constant, you can write it as like this, right? Now, in the next step, I'm going to use independence. So in this step, I'm using independence. So using independence, you can write listen guys, please. So in the step from this step, this line to this line, I have used independence, right? Now, you know that we are assuming that the variance of every xi is sigma squared. So this is sigma squared. Okay? So this becomes n times sigma squared, which is sigma squared divided by n. All right? So do you see what I have done? Or do you have any questions on this, guys? Is this kind of clear to all of you or not? Yes? Any questions? So in the line from this line to this line, I have used independence. But in deriving the expectation, I did not have to use independence. Right? All right, guys. I'll see you on Monday. If you have tutorial today, I will see you this afternoon. If you have completed the quiz 1, could you please send it to me now? Also, if you don't have a copy of this, hello? If you don't have a copy of this, could you please come and see me now? All right, thank you, sir.
Is that a copy of quiz 2?
No. No, it's what I gave out on Monday.
Random sample equal to random variable.
No. Random sample is a sequence of random variables that are independent and identically distributed. Yeah.
Okay.
Yeah. Oh, you said?
I think I was when they said the copy of the notes.
Yeah, it's here. Everything is here, sir. These are the lecture notes. This is quiz 1. This is the distributions, and this is the syllabus. Yes, you want the notes? Yeah. Yes. You want this, sir? How are you? You want this? What? I'll give it to you on Monday. On Monday. Monday is the deadline, right? Yeah, I'll give it to you on Monday. No, I will email it to you. I will email the script to you. Okay. Thank you. Thank you. Do you have the notes? Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Yeah. Thank you. Thank you, sir. Do you have this, guys?
Yeah. Is that the second one?
No, it's the one I gave out on Monday. Yeah. Do you have this, guys? Yeah. Okay. Thank you. Thank you. Thank you, man. Do you have this one? No. I gave out on Monday. Sorry about the delay. Yeah. Thank you. You want to ask a question? You want to see me this afternoon?
No, on this.
Okay, yeah. You can do it this afternoon. Yeah. Sorry. Thank you. Thank you, ma'am. Thank you. Thank you, sir.
Copy.
Yeah. No, the whole thing. This is, I gave out on Monday, sir. Thank you, sir. Thank you, sir. Thank you, sir. Thank you. Thank you. Thank you. Thank you, sir. Thank you. Thank you. Thank you. Thank you. Thank you. You guys got the copy of the notes, guys? This one?
Can I get two of those?
Yeah, sure. As many as you want.
Thank you very much.
Yeah. You guys got a copy of this? I gave it on Monday.
Oh, yeah.
Okay. Thank you. Hello, sir. You okay? Good. You have a copy of this, sir? Yeah, I do. Oh, okay, good. Sorry, guys, about the delay.
Don't worry.
I just...
No, we're just...
Oh, okay. Thank you. Sorry. I need to collect all this. Sorry. Which department are you from? Politics. That's interesting. This is yours or not? Is it mine?
No, I think that must be yours, yeah.
Oh, okay.
This is a different room. It's fine, it's interesting.
See you guys. Bye.
Yeah, you probably just presume like they're from someone. Like you just think, oh, they're not.
Excuse me.
All right.
Sorry.